The views and opinions expressed are those of the presenters and do not necessarily reflect the official policy or position of any company. Any content provided should be considered their opinion and are not intended to be interpreted as an endorsement. Today's topic is a look into the life of a scientist solving a problem. Welcome to our Solutions for NanoAnalysis podcast, brought to you by Bruker NanoAnalysis. We look forward to bringing you a new podcast regularly. My name is Cody Morton. I'm a marketing communications specialist at Bruker NanoAnalysis and an information enthusiast. If you like to learn from specialists in their field and hear what technologies are solving their problems, you will enjoy this podcast. Every session, we will focus on a different problem that our colleagues face in the lab and in the field. Some of the solutions will be a variation of ideas you may have heard before or even worked with. We will bring you these topics in a new and interesting way and introduce you to updated and thought-provoking results. We will talk about how the problem was dealt with in the past and what we're doing to solve the problem now and perhaps even envision future solutions. Join us as we talk solutions with a variety of scientists and technicians in many different industries in the Solutions for NanoAnalysis podcast. Today, we are joined by senior scientist Dr. Kristin Bunker with our technology partner, the R.J. Lee Group, and her colleague, Dr. Marit Meyer from the NASA Glenn Research Center. Thank you for joining us today. Kristin, would you tell us who you are, what you do at R.J. Lee Group?
My name is Kristin Bunker, and I am a senior scientist at R.J. Lee Group. My PhD is in materials science and engineering with a focus in high-resolution electron microscopy. But here at R.J. Lee Group, I'm in the nanotechnology and environmental group, and the types of projects that we focus on range from advanced materials to environmental to engineered nanomaterials.
So a little bit of what gets thrown at you is what you're working on today.
Yes.
Type of thing.
Yep.
Excellent. And Marit, you're with NASA, the NASA Glenn Group. You're in Ohio?
Yes, we're in Cleveland, Ohio.
And tell us what you do with NASA in a nutshell.
Well, at NASA, I am an aerosol scientist, and my primary work area is in life support systems, that is keeping humans alive in space missions. And part of keeping them alive and happy is having good breathable air. And my background is I have a master's and a bachelor's in mechanical engineering, and then I got a PhD in aerosol science, more or less. So I have kind of that chemical engineering, environmental engineering slant now. So I work with particles on the space station in the indoor cabin environment. And yeah, particles is what I'm all about.
Excellent. What made you interested in science as a kid?
Well, I've always been a very practical person. I always, want to solve problems. I love the challenge of math. I liked looking at patterns, looking at mazes, and I did dream of inventing things. So kind of that led me to the mechanical engineering major as an undergraduate.
If you weren't doing this job, what would you be doing? What's your dream job?
Well, I probably would be a world traveler and a language learner. So I don't know if you can get paid for that, but it would be really fun and it would be challenging. And I love to connect with people from other cultures.
So, Marit, what is the problem that we're solving today?
Well, my main task is to characterize the airborne particles that are in the spacecraft cabin, and to find and develop technologies to measure these particles. Like I said, I want to maintain a healthy, breathable environment for astronauts. And we're not just talking about missions close to Earth, like the International Space Station is in low Earth orbit. But when we go beyond, when we go to the moon or eventually to Mars, air quality is really important. You can't just open the windows. You can't get fresh air very easily. So keeping that environment free of particles is very important, and being able to measure them.
Excellent. What's the question I have is what's the history behind the problem? But it almost seems like breathing's important, so there's not really a history behind the problem. But how would you answer that question? What's the history behind the problem?
Well, so far, there hasn't really been a spacecraft that had particle monitoring for air quality. And that's because the toxicologists and the environmental scientists have always considered the gaseous contaminants to be much more dangerous to astronauts. So they prioritized a side of maintaining a clean and good atmosphere for them to breathe. But now we're looking to going to the moon, and we really need to be able to measure lunar dust if it enters the cabin as a contaminant. Lunar dust is hazardous to humans for inhaling. And so it's a priority now for the Artemis mission that we're going to put the first woman and the first person of color on the moon by 2024. That's our goal. We have to be able to monitor lunar dust in the habitable spaces. And when you are on the International Space Station, there's no gravity. So really large particles can become airborne and stay in the air, floating around in the breathing zone. There's a lot of unique sources of particles we don't have on Earth. And before I find, an instrument to measure particles the way I want, I need to know what I'll be measuring, which is why we did an aerosol sampling experiment on the International Space Station, and we were able to bring back samples and do microscopy on the particles that we collected there.
And is that where the technology we're talking about today plays in with that experiment?
Yes.
Okay.
Yes. So the experiment was first characterize what's floating around so that you can pick the right instrument and design something to measure those sizes and those features of particles.
So how did people approach this technology, or how did people approach this problem before the technology studies and the technology advancements? Just big filters don't do it?
Yeah, the spacecraft so far have been designed with some very, very strong and well-designed filtration systems. And so they counted on the filtration working, and so far it has worked. There are about 8 to 10 air changes per hour on the space station, which is super, super clean air. But if you were on a lunar mission, there could be a leak or some other contamination event where you could get a lunar dust coming into the habitable spaces, and it could make the inhalable dust concentration go to a dangerous level. So the astronauts need to know this right away, which is why particulate monitoring is so important. As for the International Space Station, before I did my sampling experiment, nobody really knew what was floating around up there. They just said, we know our filtration is good. And I said, well, let's see what we're going to bring back. Once I got the samples back and had the microscopy analyses done, I could show stakeholders at NASA the kinds of things that really are floating around in the air, really unique materials, unique morphologies. It was very useful for determining where these particles are coming from, what kind of trends in particle emissions there were going on. And some of these were useful for saying, okay, we can reduce this particle source by doing X, Y, Z. Other examples of what we found were just fascinating. But the good news is that we didn't discover anything really hazardous or problematic in the samples.
Does that mean that they were right, that they didn't need to worry about it since there wasn't really anything hazardous?
I would say they were right about the space station, but they would not be right about the lunar mission.
Okay.
So
it's really a whole different morphology. It's made up of different stuff.
Yes. And when we get to the moon, we're going to have typical cabin dust potentially mixed with lunar dust contamination. So knowing the qualities of the one before you mix in the dangerous one is an important task to tackle.
On the original, you may not know the answer to this, but on the original missions where lunar dust was actually collected, say, accidentally or on purpose, how did they deal with it?
Well, they got a lot of complaints from the astronauts and talking about how it was very abrasive and it stuck into their spacesuit material and was causing wear. And they were almost to the limit of how safe they felt in their suits after a few different tours outside of the lander. And also, there was eye irritation and just some, respirable kind of difficulties. So they tried to do something about it in terms of increasing cleaning protocols for the subsequent Apollo missions. But it wasn't fully characterized until they got the lunar samples back.
Okay.
And they studied those a lot.
Very cool. I could ask about 100 questions, but I want to get on track with what we're talking about today. So you had gotten the samples and then sent them for microscopy testing. Is that where the RJ Lee group comes in?
Yes, RJ Lee group partnered with me on the aerosol sampling experiment. Providing the samplers, kind of a design of the passive sampler was a joint effort. It was really fun, creative thing to solve together. And their microscopy on the samples after they were returned has been amazing. Just amazing to me to see so many unique particles that I never dreamed of. And they've told me that these are the most unique samples they've ever worked with as well. But, when we started out, we didn't even know whether we're going to collect enough to look at or whether the sampler would be, just right. So the first time when we opened those samples, I was at RJ Lee group and it just blew my mind. I couldn't sleep that night.
Oh,
it was so successful.
Oh, awesome. Now, Kristin, were you involved with this running of the samples with the microscopy steps?
Like Marit said, it was kind of a joint collaboration. And in terms of the samplers themselves, when we were designing that and thinking of how we wanted to sample, we really had electron microscopy in mind. We knew that that's the technique that we wanted to do because you can look at particle by particle, you can look at morphology, you can look at chemistry and particle association. So we knew that there was so much we could learn if we had material on the samples. And so the sampler was essentially an aluminum box that had 5 kind of drawers, that each drawer was a sample. And we put a carbon substrate on it to collect the particles directly. And we did that so that we'd have a nice background for microscopy and that we could put the entire sampler into the microscopes. We didn't have to touch it too much or handle it too much. And so, so that worked out really well. And then, like Marit said, when the samples came back to Earth for RJ Lee Group, our team was just so excited. The box arrives at RJ Lee Group and it has a big NASA sticker on it that says, critical space item. And we just took it into our conference room and waited for Marit to come. When she did come to RJ Lee Group and we opened it up, the first thing we did, we had an optical microscope ready and we documented everything. And like she said, she was a little worried that there wasn't going to be anything on them. But right when we opened them, depending on the location, you'd see fibers and particles, and we knew we were going to get some good data. So I can talk a little bit about how we decided what we were going to do if you like.
Absolutely. I think everybody that listens to a microscopy podcast would have experience with looking at a sample and deciding how to proceed. But not everybody has looked at a sample from outer space. How do you proceed?
Well, the first thing that we really did was, like I said, documented everything, knew we had particles, and then we put it into the electron microscope. And like Marit, again, already mentioned, they were the most unique samples that we had ever worked with. There were more metals on these samples than we had ever seen. And that was just super interesting. And so one of the things that we wanted to do was to understand those metals better. And so the plan then was to get a better handle on that was really to do automated particle analysis with IntelliSim, which, you're not only collecting images, but you're collecting spectra from hundreds to thousands of particles, depending on the sample. And that's what we did. We decided to do, which we ended up kind of terming the metal analysis, and really looked at particles with titanium and above. And I mean, Marit, maybe you can speak to this and some of the different unique elements that you thought were interesting or surprising.
It's funny because I would tell people at NASA, oh, I found gold on the space station, and they said, you could be rich. So then I had to add a note that's saying not everything we found is statistically significant. We found like 2 or 3 particles with gold in them, but it is an amazing array of particles. We've looked at the ones that are a little more hazardous, like cadmium and bromine and lead, and we know that the concentrations are extremely low and not a problem for the astronauts. But pretty much whatever goes up there, we're going to find it in particles. And that's so surprising, because it seems like on Earth you wouldn't have those things airborne as much because they settle. They have your particles settle very quickly, and like I said, in microgravity, you can't count on gravity cleaning the air for you. You have to wait for that particle to float around following the ventilation system flow until it lands on a filter.
Yeah, and I would just say too, when we did the automated analysis and you get all of this wealth of data, you're combining images with chemistry, and our goal was really that when Marit looks at this, she's like, oh, well, I can maybe start figuring out the source or where some of these particles came from. And that was kind of a fun thing that we did along the way too.
So you use the IntelliSim.
Yes, it helps collect the data.
Okay.
So, and what the chemistry, the morphology, so you'll get an image of every particle, you'll get a chemistry of every particle, and then you can go back and you can review them. And when we did that, actually, with one scientist here, Tracy Lurch, was very involved in the project, and she manually kind of looked at all the data and then made classes. And I can tell you that it was the most classes of particle types that she's ever had to do. It was on the order of 70 different particle classes that she made. So that just means, is it silver rich? Is it silver bearing? Is it silver sulfur? Is it lead rich? So what types of particles? And what was nice about the IntelliSim then is that if Marit found particles of interest, like she said, oh, hey, that silver sulfur particle looks really cool, we could relocate. And we could collect high resolution images. We could collect a higher count spectrum. We could collect really nice EDS maps. So we were able to do that for her. And I think that worked out pretty well.
And then Marit, was this information that was collected, 2 questions: what you were expecting to see, and then how did you use that information, or how are you using that information?
Well, I had no idea what to expect as far as the samples. I didn't even really dream of what they would look like. So, I was thinking, just some jagged things and, maybe a little more uniform, but I didn't really imagine it. But when I saw them, a lot of these really, really strange looking particles, it made my imagination wander. So I've named this silver particle the dragon. But yeah, I mean, where does the silver come from? That the result of showing people at NASA these unique particles and the materials generates questions. And right now in the water processing system on the space station, they recycle the water from, the wet wipes and the bathroom. The heat exchanger takes humidity out of the cabin and it recycles it into potable water. On the Russian side of the space station, they use a silver biocide in their water treatment. In the ISS, on the US side, they use iodine, and they're looking to get away from iodine. So they wanted to study changing our system to a silver biocide system. And so they came to me, the water people, and said, tell us about your silver particles that you've collected in your sampling experiment. And so that launched a whole study about the quantities of silver, the morphologies, what is silver likely to be combined with in the particles I've collected. And this information was very helpful for other aspects of life support other than just particles floating in the air. It leads to other conclusions and help in guidance in designing other life support systems.
Well, we saw a lot of those. Marit did name a lot of particles, so. But I would say, I was just going to mention another kind of interesting kind of source story would be when we were looking at the samples on every single location, on every single sample, pretty much, we found these zirconium aluminum chlorine particles. And, you know, we didn't know at first what that was, but once we kind of did some research, we found out they were antiperspirant particles. And maybe Marit can talk a little bit about that.
So we were super puzzled. Antiperspirant particles collected in all 7 locations in both of our sampling experiments, 2016 and 2018. And I talked with some different logistics people at NASA in the crew clothing department, and they said, "Oh, we don't have laundry. The crew doesn't wash their clothes. They wear them until they can't stand them and throw them away. Laundry requires way too much water. We can't spare the water for laundry." So, and maybe you don't know, but when you're in microgravity, you can lose bone mass and muscle mass very quickly unless you do weight-bearing exercise. So the crew members are required to exercise at least 2 hours a day. And so every day they're getting on a treadmill that holds them down with a bungee, or they have a simulated weightlifting machine. They also have an exercise bike with no seat, because you can't sit down in microgravity, right? And so they get on these machines and they exercise for 2 hours. And before they do, they put on their exercise clothes, and they probably put on a lot of antiperspirant. And they exercise, and then they change out of their exercise clothes into their regular clothes, and they probably put on a lot of antiperspirant at that time. And by the end of the 2-week duration of their one shirt that they get to wear, there's a lot of antiperspirant caked in that shirt. And you can imagine, just by moving their arms back and forth, there's probably a poof of antiperspirant particles that come off of it. So it's a little bit of a disgusting story, but it's reality. These are the sacrifices in space travel. You can't have everything that you have at home. No one ever imagined that there would be antiperspirant particles floating in every area of the space station.
Yeah.
And Marit has a nice slide up here showing a nice image, and then an area scan on the top showing the different chemistries. But then the nice thing about when we would be able to relocate with the EDS system, we could do spot modes, and you can see that, you can see the bright different regions. We could do a point mode and actually get chemistry from different specific locations within the particle. And we did find a lot of complex particles with embedded, like carbon matrix with embedded particles or inclusions. And again, another reason that it was just fascinating and the most interesting samples that we've seen.
Now, what makes the IntelliSim solution so beneficial to this sort of situation?
One thing is just the sheer number. If you're using the IntelliSim and you're doing automated particle analysis, I don't know how many particles we collected, but depending on the sample, it was is definitely in the thousands on each sample. And if you take into consideration how long the samples ran in an automated mode, it was anywhere from like 10 to 15 hours or something. So, that's something we couldn't do manually.
Yeah.
We wouldn't be able to get that much information. And Marit has a slide up here just showing the depth and how much information you can get in terms of morphology, chemistry, quantitative data from the EDS system. So yeah, it's just something that we would never have been able to do manually. And this just really gave Marit a full view of the different types of particles that were there. And so if she would find, if she'd be looking through something like the slide that she's showing now, and she'd see something of interest like that lead particle, she'd say, well, let's look and see how many lead particles are there like that. So it gave Marit as the program manager, the ability to kind of be more involved and understand the data and request things from us. And yeah.
Now, is this evaluation, this project finished, or is it an ongoing microscopy project? I'm sure Marit is still working with all the data and all of the information, but from a scanning and evaluating and analyzing, is that part finished?
Well, let me talk about that. When I first got the particle samples and the analyses back from RJ Lee Group, I was totally smitten by the morphologies and the uniqueness of the particles. But over time, I've had to delve into different particle classes that were of interest to NASA stakeholders. And, it's such a goldmine of data that we're still exploiting it in ongoing projects, just the data from the 2 different sampling experiments, just the wealth of data that's in the IntelliSem output. But we do plan to repeat the sampling experiment probably within the coming year. So we'll have a whole nother set of cool things to look at and compare, because it is a snapshot. It's a window in time on air quality in the ISS. And it's not a constant environment by any means. There's always new experiment payloads that are going up there with unique materials. And so we did see a lot of variety between the 2016 and 2018 data sets. And part of what we're doing right now is kind of comparing both and seeing, this one had a lot more silver in the air. This one had a lot more something else. So there's a lot that's yet to be exploited in this data set.
Marit, I had asked you earlier about what you're doing with this information. How does the information that you've gained from this project going to work into your lunar project that we had started talking about? Or is it just 2 different things?
No. So the way it works is we actually have to understand concentrations of lunar dust separate from concentrations of normal cabin dust. Mm-hmm. So first of all, characterizing the cabin dust the best we can is a really good start. We want to calibrate an instrument, an optical light scattering aerosol instrument, to measure this cabin dust. And then we can use those results for when we get to the lunar missions to, we know what to expect from the background of humans in a spacecraft. Then the lunar dust is going to be an added source on top of that. So there are a number of technologies that we're looking into, including machine learning, that could distinguish a different type of particle from normal cabin dust.
So, Kristin, I guess my question for you is, where is this technology going from a microscopy standpoint? Will it get more detailed or just faster, a little bit of both? What do you think? I'm not making you promise anything.
We do have a team of developers that are constantly working on IntelliSem to improve it and make it more user-friendly and add features that the users request. And right now, a couple different groups within NASA we're just currently getting them up and running, and they'll be able to, provide input to us too on what improvements they might want or what features they might want.
Marit, were there any other fascinating or interesting results that you were surprised by with this ongoing project? Or is there something that you're hoping to see in the next round of studies that you want to see more of or try to get to the bottom of?
Well, I think one thing that's so unique about these particle samples, which is also very hard to convey to people who don't know, a lot about particles and aerosols, is that a lot of these multi-component particles have all different kinds of little embedded metals, inclusions within like a carbonaceous matrix, for example. And we're not really sure about the formation mechanisms of these agglomerates. Sometimes you wonder, is this part of some parent material that has like some complex composition, or were a lot of these really tiny metal particles airborne and then they kind of combined through their electrostatic state? It's pretty charged environment up on the spacecraft because of radiation and because of how the particles are generated with, wear or friction. And so maybe they're like all individual and then they kind of glom together after they've been airborne. So we had to look, when we looked at the metals, we looked at individual metal inclusions. So when we talk about, we had, 80,000 particles in the 2018 sampling experiment, those aren't all individual particles. Those are individual metal particles that we analyzed with IntelliSem because it makes more sense to look at it that way, but then you can see how they're combined together in the workbench, and also in, high resolution micrographs show you a lot of that stuff as well.
And she has a nice example on the screen now that has a name. That's the T particle, or the Thor particle, right, Marit?
Thor's hammer.
Yeah.
Was there any other surprising things?
Mm-hmm.
I mean, I can think of a couple other particle types.
Kristin, what did you
Marit,
think of?
she can chime in, but we found a lot of salt in different, especially in the eating location. We found some titanium dioxide that could be from some kind of, I don't know if it would be makeup, but some kind of product. And then what we found, stainless steel in the shards, kind of in the exercise area. I'm trying to think of any other kind of particle types that we found like that we could kind of source.
Yeah.
We saw a lot of fiberglass. Fiberglass particles, they're like little sticks, like perfect rods. And so I've had some student interns analyze just kind of by manual microscopy, looking for these really recognizable particles and cataloging them and showing the quantity by, each location where we sampled. So we could see, like, in one particular area of the space station, there's a whole lot of fiberglass. There's a source there that's irregularly abraded, and the particles the fiberglass fibers just come off. And, it's really striking when you can see it broken down like that.
Was there anything inside the space station from the outside? Was there contaminants from the outside that proved that their moon boots didn't get dusted off or something?
No, we didn't have any evidence. I mean, frankly, I wouldn't be able to recognize what's outside, but there's pretty much like hardly anything out there in low Earth orbit. But, once we get to the moon, definitely there will be like contaminant back and forth all over, and Mars as well, where you're going to actually have, people walking on a surface and then coming in with their suits covered with stuff. And dust mitigation is like a really big ongoing effort right now at NASA. We have lots of people working on it because we want to prevent as much dust contamination as possible, but we know we won't be able to prevent all of it.
Now, while we're finishing up, Marit, you had provided some links that we could point our listeners to. Would you mind just telling us where those links are going, or what kind of information you'll get when you click a link?
Well, I have some conference papers, which is for the International Conference on Environmental Systems, which is the main life support systems conference for the space community, the international space community. And those are open access. So links will go to those conference papers. That's where all of the stakeholders, anyone interested in life support, air quality, water quality, they go to that conference. And they're all on our NASA server as well. And also my ResearchGate profile has publications that people can look for.
Kristin, what about research that you guys have done? Have you released any white papers or studies on this project or the IntelliSim?
Well, we do have some other publications on IntelliSim that I could provide. We have not done a publication on the work that we've done with Marit, but we really should.
When is the next round of studies supposed to happen?
No, so it depends on the mission that we can hitch a ride on. So there are cargo vehicles that go up that bring up experiment payloads. And if we get a ride up on one of those, we can do the experiment, and then we have to wait till the next ride comes down. The thing is that there's way more rides up than there are rides down, because not all of the vehicles are reusable. A lot of them are one-time use. So once they get all the cargo off of them, some fresh fruit, supplies, new clothing, they pack the vehicle full of trash, and then it just kind of falls into the atmosphere and burns up into smithereens. So that's how they dispose of their trash right now. And so because there's only, a few vehicles that are returned that bring samples and things back, it's kind of a precious real estate there. And we may have to wait to get them back. But my goal is to go up and come back on the same reusable vehicle. So we'll see if we can manage that.
Fingers crossed. The moon mission that's in works, what do you think that's going to lead to? If you just had a crystal ball, Marit says, this is what's going to happen, what do you think?
I think the intent of the Artemis missions to the moon is to help us learn how to live in a faraway place with a very harsh environment. And that will give us a chance to prove out a lot of the technologies that we need. And then it will enable us to go to farther destinations like Mars. And in my crystal ball, I see people living in communities on the moon or on Mars someday, but not in my lifetime, probably.
Thank you to our speakers today. During today's discussion, we talked about the IntelliSim technology that used Bruker Quantex EDS. Find out more about the EDS technology in our show notes. If you would like more information about today's topic or to submit a topic idea, please email info.bna@bruker.com. You can also check out more information in today's show notes. Join us next time as we look at new solutions with more scientists and technicians in all sorts of industries.